Okay, I'll get started. Well, thank you, Matt, for the introduction, and thank you for everyone for having me here. It's lovely to present to you all. So I will get started on my talk. So I'd like to start by giving a bit of motivation and aim for my talk. So in recent years, the Fields medalist Vaughan Jones showed how to obtain unitary representations of what's called Richard Thompson's group F by considering functors coming from the category of binary forests into the category of Hilbert spaces, in which the morphisms are isometries. He then generalized this method, allowing for the replacement of this category F and the category of Hilbert spaces by more general categories, thus expanding the scope of the construction. So my aim for this talk is really to give an exposition of this method of constructing group representations and some potential directions it can be taken in. So in order to start this, I'd like to introduce the category of binary forests. So the objects of this category are the natural numbers and the morphisms are binary forests. So let's see an example. Basically, a binary forest is a bunch of vertices arranged horizontally. In this case, I'll draw 3. And these vertices are called roots. And coming up out of these roots, we have binary trees. So something that looks like this, maybe. And we could have something also that just comes directly up, and we might have something that just only branches off once. But whenever we branch off, it can only branch into 2, hence the name binary. So this is a binary forest. We have a bunch of binary trees standing next to each other. And as we can see, there are some endpoints at the top, and these are called leaves. So something like this. These two things are leaves. And we want to see this as a morphism in some category. And the way that we do this, remembering that our objects are natural numbers, is that we consider this as a morphism from the number of roots to the number of leaves. So in this case, we have a morphism from 3 to 6. And the way that composition works in this category is via stacking. So if I take a morphism from 2 to 3, let's say, so 2 to 3, and a morphism from 3 to 4. So this is from 3 to 4. Then this is going to give me a morphism from 2 to 4 by stacking. So I take this tree, I draw it. Maybe I'll give myself a bit more room. But I'll draw this tree, and then on top of it, maybe I will put, so yeah, on top of it, I'll put the tree on the right, and that's going to give me this. And this is going to end up being a morphism from 2 to 4. So that's how composition works. And the identities in this category are given by the following. So the identity of a natural number n is going to be just n vertical lines stacked next to each other. So these are going to act as our identities. And all of this data forms a category and called the category of binary forests, which we're denoting by F, which is pretty neat. Okay, so a nice property of this category is that it admits what's called the calculus of fractions at the object 1. And what this means is that morphisms with source 1, so morphisms coming out of 1, or binary trees, satisfy certain technical properties that lead us on to our next point. So what this calculus of fractions gives us is a group F of fractions of morphisms in this category of binary forests, in which both the numerator and the denominator have source 1. So we have a tree on the top and a tree on the bottom. And these trees have common target or the same number of leaves. So let's see an example of an element of this group. We have a fraction, and let's say in the numerator, we have a tree with 3 leaves. So in the denominator, we should also have a tree with 3 leaves. So the other tree with 3 leaves is this. And this is going to be an example of our group F. And a crucial identity that this group satisfies is that A over B times B over C is always equal to A over C. And this is really why we call it a group of fractions. So this group F is called Richard Thompson's group. And it's accrued a lot of interest over the years. It's popped up in all sorts of different fields. But like a really notable open problem about this group is regarding its amenability. So is there a left invariant finitely additive probability measure on this group? Well, nobody knows, and it's quite a tough nut to crack. Okay, so we've just seen that from our category of binary forests, we obtain a group F of fractions of trees. And what Jones did was he showed how to take a functor coming from this category of binary forests, going into the Hilbert spaces, and then from this functor obtaining Hilbert space, x, phi, depending on the functor, and a group action of our group of fractions onto this Hilbert space. And it turns out that this group action is compatible with the Hilbert space structure of our Hilbert space x, phi. And what this ends up giving us is a homomorphism from our group of fractions to the automorphism group of this Hilbert space in this category of Hilbert spaces, where we remember that the morphisms are isometries. So elements of this automorphism group are isometries, and that's why we get actually a unitary representation of Thompson's group F, our group of fractions. But it should be noted that this construction relies on the fact that there's a forgetful functor from the category of Hilbert spaces to the category of sets. So Hilbert spaces are sets with extra structure. And the way that this construction goes is you literally take an element of your group and a vector in your Hilbert space, and you define what it means for the group element to act on this vector. And this is going to give you an element of your Hilbert space. So Jones actually noticed that you can replace any, you can replace the category of binary forests with any category C admitting what's called this calculus of fractions at a certain object. And this category and this object then give you a group of fractions, much like we just saw. In fact, our group F that we saw is what you get in the case where your category C is the category of binary forests and your object is 1. You also notice that you can replace a category of Hilbert spaces with many familiar categories. In this case, they're all concrete. So the category of sets, modules over a ring, category of groups, abelian groups, and Lie algebras. So what you can then do is take any functor coming from our category C with this calculus of fractions to a category D. And let's just say this category D is just one of the ones that we mentioned in the previous point. And from this, you're going to get a representation of your group of fractions in the category D that you've chosen. But again, we're dealing with concrete categories or concrete. Yeah, so here D is a concrete category. So we're still relying on the fact that the underlying objects of this target category of the functor are sets. Okay, so what if the objects of D aren't sets? So maybe we want to give a more general or categorical description of what's happening. So we can actually do this in the case where we have a calculus of fractions at every single object, not just one. So if our category D, so remember we have our functor coming from C to D, if our category D is co-complete, then we can actually form what's called the left Kahn extension of our functor phi along this functor P called the localization functor here. And this localization category has the exact same objects as the category C, as you can see here. And the morphisms of this localization are fractions of morphisms of the category C. And you can think of this localization C hat as the best approximation to the category C in which every morphism is invertible. So in particular, this localization is a groupoid. So if we then restrict this Kahn extension to the endomorphism set of any object of your choice, right? This is going to be a group and it's going to have fractions because the morphisms of the localizations are fractions of morphisms of the category C. So we restrict to this group and then we're going to get a group representation in the category D. And this turns out to be exactly the representation of the group of fractions that we were just talking about. So this is quite a nice categorical description of what's happening when we have a calculus of fractions at every object. And something that I would like to think about is what if we don't have a calculus of fractions at every object, maybe just one object? Can we still get our group, the representation of our group of fractions by restricting this Kahn extension? So I'm not sure about that at this point. Another natural question to ask is what choices of the category C and the functor phi make interesting things happen? And a partial answer to this question is by taking our category C to be the category of binary forests that we saw earlier, and phi to be a monoidal functor. But to have a monoidal functor, we need a monoidal structure in this category of binary forests. So let's see how that works. So on objects, remember the objects of F are natural numbers. So we just define an object M tensored with an object N just to be their sum. And we define the tensor of two morphisms. So let's take an example like this. Maybe I'll do this. So what do we find the tensor? What do we define the tensor of the morphisms to be? Well, we just kind of forget that the symbol's there to begin with and just put them next to each other. So So this ends up giving us a monoidal structure in our category of binary forests. And by a monoidal functor, we just mean one that preserves this tensor product. So it turns out that such a functor phi is determined by its action on the object 1, which is kind of not too difficult to see. So if we look at what our functor does to an object n, where n is a natural number, well, you can see n as 1 tensored with itself a bunch of times, right? Right. And because this functor preserves tensors, this is just going to be phi of 1 tensored with itself n times. But not as easy to see is that also for morphisms, our functor is also determined by its action on this tree with 1 root and 2 leaves that I've called y here. So y is literally the tree with 1 root and 2 leaves. And this is a morphism from phi of 1 to phi of 1 tensor phi of 1. So from this, we kind of see that monoidal functors from our category of binary forests to a certain category D, monoidal category D. These are in one-to-one correspondence with the choice of an object of the category D and a morphism from the object to the object tensored with itself. This is kind of a nice way to actually generate these monoidal functors and hence representations. So let's see let's see this in practice. So I'd like to go over the case in which the target of our functor is the category of groups. We certainly have a monoidal structure on the category of groups given by the product. And from what we just saw, if we take a group homomorphism from a group gamma to the product with itself, this is going to give us a monoidal functor from the category of binary forests to the category of groups. And from what we saw earlier again, this is going to give us a group homomorphism from the group of fractions, which in this case is Thompson's group, to the automorphism group of some group x phi. And from this, we can form the semi-direct product of this x phi with our group of fractions. So let's just see what we've done so far. We've taken a group homomorphism alpha, and from this, we've created a new group. And this new group actually ends up being the group of fractions of a certain category E. This is something that my PhD supervisor actually worked out. So we've made this new group, and we can study it via functors coming out of this category that it's the group of fractions of. So yeah, in summary, we can use this Jones method of obtaining group actions to firstly create new groups, and then we can study these new groups that we've generated using the same techniques, which is pretty neat. And finally, I'd like to talk about what happens when you have like a contravariant functor, and this is currently what I'm thinking about. So yeah, what if our functor is actually contravariant? So it turns out that you still get a representation of your group of fractions in the category D. And what I'm doing right now actually is I'm starting with an isometry coming from a Hilbert space tensored with itself to the Hilbert space itself. And this is going to give a monoidal functor from the opposite category of the category of binary forests to the category of Hilbert spaces. Before we had something that looked like A to A tensor A, but now we have a contravariant functor, so we're going to look at stuff tensored with itself to the thing, the object, right? So this is a bit of a typo. This is not meant to be a math calgy, but let's ignore that. So this gives a unitary representation of our group of fractions in a Hilbert space H infinity, and this Hilbert space H infinity is actually isometrically embeds into our Hilbert space that we started with. And right now I'm just thinking about some basic questions about this Hilbert space, like is our embedding actually surjective? So is this Hilbert space that we get a unitary representation on actually isomorphic to the Hilbert space that we started with? Because that would be pretty cool. Like we'd take a Hilbert space and an isometry of this form, and then we get a unitary representation of Thompson's group over that same Hilbert space. And I would also like to know things like, when is this representation irreducible? So yeah, that's basically what I'm thinking about right now. But we don't have to work with Hilbert spaces, right? We could work with groups. We could take a group homomorphism like alpha from the product to itself. And if our group is abelian, this could just be given by multiplication. Then this is going to give us a new group, a semi-direct product, and then we can study what that semi-direct product looks like using this Jones construction. But yeah, So just a summary of my talk and what we've really been looking at. Really what I would like you to take away from this talk is that a category and an object give us a group of fractions, and then a functor coming from this category into another category gives us a group action or a representation in the category, in the target category. And choosing our category and our object and our functor wisely makes interesting things happen. And I'll just draw a diagram summarizing like all of this stuff. So I like to draw this diagram where we have a category, and then this gives us a group down here. And then we have a functor coming into another category. And this functor actually gives us an object of D, and then our group acts on it. And yeah, that's about all I have to say. Thank you, everybody, for listening.
Let's all thank Christian for a great talk.